tell me how you guys approached question 1. Thank you, sir. And I'm writing a note to Coach Stewart. Great. How did you guys approach number 1? Chromium 54. What does that chromium dash 54 mean?
Oh, that's that one.
Okay, that's the atomic mass. It's an isotope of chromium. Okay, you find chromium, atomic number what? 24. Okay. If atomic number 24 is what you see on the periodic table, what does that atomic number tell you? 24 protons. Sorry, I'm multitasking. Today's the 13th. And all right, thanks, Ishmael. So if the atomic number is 24. Sorry, I'm off track here. And 24 is your proton number. What does that 54 totally represent? Atomic mass, which is protons plus neutrons. So 54 is neutrons plus protons. Subtract that, you get 30 neutrons. And so then you just had to backtrack to figure out who else had 30 neutrons in this case. So it was who? Manganese. My periodic table's down. So manganese is atomic number 25. That means 25 protons, and then 55 minus 25 is 30 neutrons. So what's not consisting as a part of the mass? Electrons. We should pick up the packet I was printing out. It's in the out box. Hey, Caleb. Come on in. I thought those were alleys. I wasn't sure. All right, so back to me. All right, let's go, Ruchi. Scooch in here, girl. Good to see you. Thanks. All right, so question 2. Based on the average atomic mass of 32.06, it's consisting of 3 isotopes, sulfur 32, 33, and 34. Based on this information, which is most correct, would you guys say? Why B?
Because it's 32.6, meaning that 32 was going in because it's closest to 32.
Okay, so the overall average mass is going to be more representative of that isotope. So 32.06 means I have mostly isotope 32, just a smidgen of 33 and a 34, which pulls the average higher. So you're probably thinking like 98% or so sulfur 32. So the predominant species controls the average. Just like if you got all A's in all your classes in 1D, your average wouldn't drop entirely, right? It would drop a teeny bit because the predominant species is the A++ student you are. Okay, goals. All right, this is what I was hoping I would feel for where we were. 3, about half of us missed, so here we go. Gallium's atomic number what? Gallium 31. So I want to see where you are here, and then we're going to kind of go from there. Okay, so magnets. All right, so if you're here, you're looking at gallium. Gallium's here. I need to go row by row by row by row, accounting at the building of this atom by its electrons and its electron orbitals. The orbitals are s orbitals, p orbitals, d orbitals, and f orbitals. Those are all based on Schrodinger, Heisenberg, Einstein, Planck, a couple of other guys who came all together to create the quantum mechanical model or the quantum theory. That's way after Bohr's model, which doesn't call them orbitals, he calls them, say again? Okay, the electron shells is actually a term that we'll use more consistently now to modern term. We haven't used orbits, and that's what the Bohr model looks like on the honors team reference sheet you guys got on your exam and all that. So that's a little different. That doesn't have SPDF. The quantum mechanical model does. So if you're trying to figure out what the straight up electron configuration of gallium is, you say 1s. You got me?
1s2.
Come on, 1s2.
2s2.
1s2, 2s2. Stop. Where am I at? That's 1s2. Beryllium. Okay. 2p6 gets me from second energy level p block through neon. 3s2. And then scooch over to the p block, 3p6. 4s2, stop there, pause. So I currently am at calcium. How many electrons does calcium have?
2.
Don't you count these. Go back to calcium. Point at it. It's atomic number 20, right? 20 protons should negate 20 electrons to create a neutral species, a neutral calcium. So 20 electrons, 20 protons, simply because atomic number is 20. You can quickly check this by doing tens. 10, 10. Okay, yeah, there's 20 there. Okay, oh, and then where are these electrons shown in the electron configuration? As what? So what number here represents the number of electrons? The exponent. Sorry, this is a 1. We're saying I'm in the first energy level. The S is like, I'm in the S block, or I'm in the S orbital of that first energy level. And the 2 is like, I've got 2 electrons. And then I've got 2 electrons, and then I've got 6 electrons, because I have so many orbitals I can fill. And I've got 2, plus these 6, plus these 2. Okay, so there we go. So far, I've got 20 electrons I've counted for. Now when I hit D block, which is the transition level group, it has a weird way of relating energies. It's not in the 4th energy level anymore because we're in the 4th energy level according to the 4th period. This is where we drop 1. We do n minus 1. You run this a little bit. We subtract 1, and now we're doing 3D. 3D what? 3D 10 because there are 10 electrons across to zinc. Now I'm at gallium, but I pick back up to the 4th energy level, and I put 4p1. How many electrons total? 31. Atomic number 31. That's how you know you're not in the ion form, you're in the elemental state, which is just this normal number of electrons. We'll hit the electron configuration through examples today and talk about some of those exceptions to the rules. But I generally follow the electron configuration periodic table method. There's another method. It's called the diagonal off-ball principle rule. Does anybody remember doing diagonals? Okay, don't worry about it. That's how I learned it. I had no idea what I was doing in chem, in AP Chem, until I started teaching it. That's when I learned how to actually write electron configuration. I got through life. I'm not saying it was easy, but you know. But I really want you to understand it because I remember that was the first thing I taught when I. Oh, the answer was I'm sorry. P was it P number of P electrons?
Yeah.
So it should be 13, right? No, sorry, 6. Yeah, 13. 6 plus 6 plus 1. Okay, so then for which of the following electron configurations corresponds to an excited state? Excited electrons mean they normally have a ground state, like the way I've written this in the order of the appropriate energies, from the lowest energy state and energy level to the highest energy level. That's ground state. It's a nice calm arrangement of electrons. So when you skip and you put something in a higher energy state, aka a higher energy level than you should, that's excited. So which of these makes no sense? YA. Okay, so you went from 1s2 to 2s2. You should have filled up the rest of the second energy level, which is 2p6, but instead you said, nope, skipping the second part of the second energy level, I'm jumping to the third energy level, and that's why it's excited. So it should be A. And then lastly, if you're taking an electron, you're moving it from 5 to 1, what should happen to energy? It should be released. All right, so who remembers 80% of that? Some of you guys had me 2 years ago, some of you guys never had me, so I know the situation was different in different classes. Poor Riley's never even seen me before. So let's work on a couple of these review things. You tell me if I go too fast. I'm literally doing almost exactly what I did in Honors Chem, but just a heightened a little bit for AP level, okay? So in the reading, you guys saw a lot with light. We're going to practice some light equations today, especially with quantifying it per mole of photons. And then do a couple calculations. So I'm taking that information and applying it hardcore today. Write down notes for me, because I need you to stay engaged because I'm going to talk a lot. Sorry, okay? So if I have this information, these are the first 3 questions on your packet. Note, these are the middle 3 questions. So I have boron 10 and boron 11. How would I find the average atomic mass of boron 10 and boron 11 given these relative abundances? Multiply the mass. I'm going to see if I can scooch this down, sorry. So the percent abundances are just showing you the relative amount of those isotopes in the world. And I don't know how they do it. They go and collect all the borons of the world and go, okay, you're a boron 10, you're a boron 11, you're a boron 10, you're a boron 11. How they do it, no one knows. But they do have to do a lot of spectra and a lot of analytical chemistry to quantify that. Okay, so tell me, Allie, one more time. So mass is in atomic mass units, AMU, times the percent as a percent. So as a decimal, pre-percent decimal. So we're not going to multiply by 19.78, I'm going to multiply by 0.1978. So when I take the mass times its percent, we're going to do the same thing for the other one. So 11 AMU atomic mass units times 0.8022. You guys have calculators? Depending on you, so let's work together here. There's a couple scattered around the room as well. What's the first one? 1.978. Please tell me that's right. Okay, so just multiply by 10. And then the last one?
Is
8.8242 AMU. Okay. So after so step 1, multiply mass by percent as a decimal. Step 2, what do I do next? Add. That's it. Do not divide by anything at the end. It's not a normal average. The normal average is you add stuff, you divide by whatever at the end. This has already been accounted for as a relative percentage, so do not add at the end. do not divide by anything at the end. So what's 8.8242 plus 1.978? Oh my gosh. Okay, so I had other stuff in my calculator. What's the answer? Anybody? 10.802. I'm stopping here for a second, okay? So this should be the average isotope mass of boron. Does any boron atom weigh that? No, that's an average that exists because it's counting for every isotope in the world of boron, but no atom actually weighs that. How would this be represented on a mass spectrum? This was on your midterm. Mass spectrum diagram. A graph. AJ? Okay, so let's do so this would be atomic mass, and on the bottom is like a 10 and 11. I was going to put AMU, so for atomic mass. Okay. So you'd have a bar here for the 80-ish, and then you'd have something here. You would have to normalize the data, but regardless. Huh? Oh, sorry. Yeah, I'm just like to listen to you guys, my bad. Okay, so something like that. So that would be your mass spectrum because you only have isotopes that weigh 10 or 11, but the average is indicative of the overall. And then what's the average atomic mass of boron? 10.801. All right. Or 10.8 something. So we're doing good. I didn't actually make that example up. Sometimes I make them up and they're wrong. Okay, so that's how you do your average percent. I'm not going to do another one like that. In terms of which is most common, we kind of just discussed that from the episode Socrative. The most common one controls the average, so who's most common here? Number 2? We got X45, X46, and X48. X45 because the average is closest to the most abundant particle. Okay, so what's the only difference between copper 65 and 63? 2 neutrons are different. How about their chemical and physical properties? Are they different? I would say yes, they are the same. Because isotopes, the only thing that differs is their mass, right? Sometimes that can change their radioactivity, which we'll talk about nuclear a little bit, but like copper 65 or copper 63, one of those nuclei are more stable than the other. I don't know which one off the top of my head, I have to do the math. But that one is more stable, but still, they're both conductors, right? List off some properties of metals. Copper is a metal, right? Ready? What are some properties? Oh, good, conductive. That's novel. What else? Malleable. Ductile. Lustrous. What else? Oh, nice. Low specific heat. I was just talking to my husband about that. What were we talking about? Oh, I had my keys in the fridge by accident in my lunchbox. And I was like, gosh, my keys are so cold. And I was like, but they'll warm up in like 3 seconds. And they did. They're just so quick at releasing heat and absorbing heat. Okay, what else? I was like, where are my keys? I put them in my lunchbox. I put them in the fridge. Okay. What else? Okay, those are good physical properties. Metals are generally able to be, they're active. What do I mean by active? Able to oxidize, meaning able to lose electrons very readily, and that's all because of their electron configurations of having a low number of valence electrons. And so that's more about their chemical reactivity. Notice that this doesn't have a different number of electrons, so therefore its chemical reactivity is very similar to the other. Good job. All right, so I'm going to do a lot of quick reviews, so you work with me here. Coulomb's law, you never learned in honors camp, but you learned a teeny tiny bit with me early in the year. Write down this equation for Coulomb's law. But you should recognize the term Coulomb, right? Coulomb referred to what earlier for us? The unit of, so it was like 96,500 coulombs per mole of electrons. Yeah?
Yes. Oh, yeah.
So that's very constant. Oh, what's it expressing? What's it showing?
Second.
What's a coulomb?
K times Q plus a Q minus D squared.
So a coulomb is a unit of charge.
Oh.
A unit of charge. So charge of an electron generally is the way it's expressed. But how does that play into this? We're talking about how charges attract each other. Okay? The only charges, and I know it's the 21st century, but in chemistry, the only charges that will attract are positives and negatives. Opposites attract. The sames repel. So what two particles would likely repel each other? Say again? Give me particles. Give me like subatomic particles. Two protons are totally gonna repel each other, right? But don't they all live in the nucleus together? So what's inside the nucleus? Protons and neutrons. Okay, why are the neutrons there? Because if protons and protons and protons were there together, it would explode. Because protons are going to repel each other, that's hence nuclear decay. Things are not stable in nucleus, they will basically break apart into smaller pieces. The neutrons are there to give some, be the peacekeepers and kind of keep the protons from annihilating each other, basically. So that's going to give you some balance there. But then as the two atoms come together, okay, so here's our nucleus. I'm just going to draw it small. So here's the electron cloud. As they come closer and closer together, what's going to happen to those electron clouds? They're eventually going to repel each other, but what if there was just enough attraction between this electron and that nucleus, and just enough attraction between this electron and that nucleus? Because those are the opposite charges, right? Positives and negatives. So if there's just enough attraction between there, they will actually form a bond. And when they form a bond, they actually form a specific bond length. I'm going to keep drawing little pictures. Okay, there was a graph that you guys have seen before where you had like this big dip. Remember this? And so you had two atoms that were far away here, and there was no attraction because they were just too far away. There's not enough opposites attracting. Over here, they were right on top of each other. So the protons of this nucleus and this nucleus are right on top of each other. Electrons were right on top of the other electrons. Lots and lots of repulsion. Do you think those are low or high energy states? If I have a lot of repulsion, a lot of just angriness between the atoms, high energy state. Like atoms do not want to be high energy. They are very unstable when they're high energy. So when there's that Goldilocks region, there's just enough attraction and just enough repulsion. They're in the Goldilocks region. That's down here. And so they're attracting just a little bit, repelling just a little bit, but it's still the perfect region. This over here is potential energy. So the potential energy drops because they have attracted to each other and they've bonded. That is the lowest energy state, is when things are bonded versus independent. Because many times when they're independent, they don't have octet or they have some other unfavorable condition about them. So that's going to give us some interesting information. But the Coulomb's law aspect comes into why do things bond, why do things attract, why do things repel. But it's more related to the fact that we have two charges, so like two ions that come together. Magnesium, what's magnesium's charge? 2. Okay, what's chlorine's charge? -1. When I take 2 times 1, that has a stronger attraction, meaning the force of attraction right here. That has a stronger attraction than, let's say, sodium. What's sodium's charge? +1, and chlorine -1. So when I throw 2 times 1 in there, that's a stronger magnitude of attraction than like 1 times 1, which is the 1 times 1 is where you put your charges in. So we will start to talk about how that relates to atoms, bonding, periodic trends. If you don't say Coulomb's law about 100 times in this unit, you're doing it wrong, okay? We will use it for an explanation for a lot of things. And I think that's, yeah, this is all. Last year we had a snow day on this day. I didn't erase all my notes. So I did a video and I sent it to everybody on snow day. So do you guys remember snow day last year, this time?
Yeah.
So we talked about cations versus anions and so forth. Okay, so atomic structure reminders. I don't think I need to do this actually. Oh, no. Let's watch this quick video. So the scientists are important because they give us perspective of where we were and where we are now. So the perspective changes just simply occur because we had more technologies, we had more equipment to discover more about the insides of the atom. So I'm going to give you guys a chance to take a quick break from me. And 9-minute video. I might speed it up a little bit so it's not 9 minutes. You want some time to work at the end though. Promise. Alright, where's my sound at? Let me see if the sound is gonna work. I just turned it on. Okay. If I were the sound, where would I be? You hear it, right? You hear that coming on. So unless somebody jacked up my headphone jack. Okay. Wow. You guys get up and review what you know about this with the atomic models. Go. Get up and talk about the scientists for a minute. There are so many scientists, you need to name them. Alright, come back to me. We're doing a Pictionary here, okay? We're just going to do Pictionary because I have no sound right now. Dang. Alright, so back to me. I'm scooching through this because I just want to show you the pictures. So, Dalton's atomic theory said atoms were indivisible. What else? All atoms are the same. Are they all the same? I mean, so are all elements of the same? So are all atoms of the same element the same? No, because there are isotopes. They have different masses, right? He said atoms were indestructible. Can we destruct an atom?
Yeah.
Truly, we can. Nuclear decay, people. We can actually do that. So that's basically Dalton's atomic theory. You guys can do some more reading on that. And then these are his things. Okay, this is JJ. What did he do? JJ Thomson. Found the electron doing the cathode ray experiment. Threw a beam through it, held a magnet to it, the beam deflected. What is it? And so like the negative end of the magnet was pointed towards the beam. Why did it deflect?
Because opposites charge. Sames repel.
Sames repel. So he then said, this is the negative end of the magnet. This has to have what in it? Something negative. He didn't have a name for it, but he said, okay, I think I'm going to call it the electron. And then somebody came after that and did the oil drop experiment. Does anybody remember that? That was Millikan, right? There's the electron beam. He did not know, but he now knows. Cathode ray tube. Okay, he had the positive and attracted. I knew it was one of them. And he developed the plum pudding model, where he said that there was just this atom, this sphere, and it had all these electrons throughout it, and all these protons throughout it because of the opposites attract and then sames repel. But he didn't actually have a location in mind. He just said, here's what's in it. That's why it looks like this. Plum pudding has the negative electrons all in the kind of the orangey color area, and positives here. Well, then who came behind him and said, nope, not right? Rutherford came and said, there's this hard, dense nucleus in the middle, via discovering it through the gold foil experiment. So it might have Rutherford next year. There's Rutherford. Okay, so alpha particles, shoot them at the gold foil, bounce back. As it bounces back, he said, there must be, actually there's probably a diagram right here, there must be So he thought they'd just go straight through and hit the detector on the other side, but then there were these deflection patterns coming back, and he's like, well, what's in the middle? And he called it the nucleus, and hence the dense location where the mass existed, which was protons. He didn't know about the neutrons yet, but he did know there was something in the middle. And then Bohr said, well, I think the electrons live in these little circular realms around the nucleus. The nucleus has to be in the middle. He's called these orbits. They were set pathways where the electrons could travel. Came to be, it was only true for hydrogen, so that's why it's called hydrogen, or the Bohr model of hydrogen. It's not really true for anything else because it's hard to say there's one location where those electrons can be. Then we got into quantum. Oh, sorry, there's a quantum, which is the quantity of energy. That's the difference between the subset of energy levels here. And then, who was that? Heisenberg? I can't remember his name. I can't remember who's who. No, these are just old white men pictures. Heisenberg, here's Heisenberg. Okay, the other one must have been de Broglie. Oh yeah, I think that's de Broglie. Yeah, de Broglie said there that you can either know the location of an electron or the speed. But the more you know about one, the less you know about the other. So my joke for you today, the joke. So, de Broglie, Heisenberg, and his friend Einstein are all riding the car together, going on a trip, and then they go, whoop, whoop. Police car pulls him over. He said, sir, do you know how fast you were going? He said, no. He said, you were going 110 miles an hour. He's like, oh, dang it, now we're lost. Because the more you know about your speed, the less you know about the location of the electron. The observer causes influence on electron behavior. Okay. You gotta know those things. You'll know those. And there's Schrodinger. He actually didn't do anything with a cat. People have this misconception. He had a thought experiment with a cat. He didn't actually have a cat or do anything with a cat. But the thought was that you can, there's an uncertainty about matter's behavior until you observe it. Once you observe it, and you force it to take one path or the other. So there are parallel universes where one decision was made in one, the alternate one was made in another. Did anybody ever watch Fringe? Olivia Dunham? Oh my God, love Olivia Dunham. If you've not watched Fringe, you have the summer. Watch it in the summer. It's addicting. It's got like some crazy instances. Okay, so he did have the wave equation, which will then kind of get into quantum mechanics. We will not talk about the wave equation too in depth because of the extreme mathematics behind it, like differential equations mathematics. And then this guy, this is Millikan. Millikan did the oil drop experiment that suggested that there was some sort of mass to electron ratio of the atom. So he expanded off J.J. Thomson's plum pudding and said, for this charge, this is the mass of those electrons. It's really infinity. Not tired. That's all I am right now. It's really small. It's negligible, but infinity tired. But the ratio is so different between the atoms, it gave us some sort of mass blinding. But really, electrons are so negligible in mass, we try to just say they're massless. All right, well, that's the narration I could give you to the video. And then I'm going to hit the highlights from here on out, because some of this is reading, and I'm not going to read to you. Oh, okay. So the ones with the stars are the ones I really want to do. You guys help me out here. Nitrogen -3. Here's your isotope notation. What's the A number mean? Atomic mass. Do I have it written here someplace? Oh, okay. So this up here, A is the the mass number. Z is the atomic number, which gives me protons. Okay, and then the charge is up here, which is going to be based on what? Changes of electrons, right? So let's do N -3. What do you know? How do you know it has 7 protons? Because that's its atomic number. Shall you change the protons? You shan't. Okay. Because if you change the protons, what have you done? Change the element, and then we have to start over, right? Do not change the protons. What was true before it got this charge? It had 7 electrons. Now it has. Is that a cation or anion? Anion. Okay. because it gained 3 electrons. How many neutrons?
Roughly 7.
Are you guessing, or are you getting an educated guess?
Well, I mean, it's 14.01.
Okay, so the atomic mass average is 14.01, so the most abundant isotope of nitrogen is what?
14.
Likely 14, because that's the closest, and so then you do 14 mass minus the 7 protons, you get 7 neutrons. But if it were in 15, you would have...
So could you technically have, like, like a nitrogen 15, I mean, it's not true, but like a nitrogen 15, nitrogen 13, and have like 51%, and 15, and 41%, and 13, and it would average
possibility,
to 15.
Yeah. Possible.
So that's why you say likely.
Likely, the most abundant one, yeah. Alright, so then, I think we're good here. Do I need to do more of these right now? Subatomic particles? I'll do them individually with you if I need to. This is review. This is mass spectra. My video will not work, so I'm not going to narrate it. I'm just going to tell you. This is the mass spectra device that we talked about way back in Unit 1. How do you quantify the number of isotopes in the world of each of these different species? Basically, they ionize the gases. They turn a sample to gas, and they ionize it. And as it comes through this beam, the beam is then deflected by a magnet. The heavier ones, they're fat, right? They're heavy. They're not going to deflect as much. They stay in more of a straight line. The light ones, you can deflect them in a heartbeat because they're just lighter. And so you have this deflection pattern that differs, and this is a detector. The detector will then count the number of hits from the light isotopes, so the lower molar mass ones, and then, or the lower number of neutrons, and then the heavier ones will kind of stay in a straighter beam. So oxygen 16, 17, 18 would hit in that pattern, and then they could quantify, oh, there was, 85% hits on the high end, which would be the oxygen 16, like 2% hits on the lower end, which would be oxygen 18. So they use a specific practice called mass spectroscopy, and that's what we did learn about. But I just want to give you a quick reminder that's how that works. You guys can read this. We're going to move on. Wow. That's all I'm going to read to you. The highlighted stuff's the most important. So if I have to ask you about subatomic particles that control reactivity, it would be protons, it would be neutrons, it would be the electrons. So that's kind of the key point of why we're hitting the electron configurations today. And the act of observing does influence behavior. That's kind of what the whole quantum mechanical theory is based upon, and Schrodinger's, Schrodinger's double slit experiment, which is a video I was going to show you, but I'm going to see if we can get the sound to work shortly. So now that we're kind of seeing the big picture, we're now narrowing down electrons. The electrons are now described to be in a specific location, and those specific locations are going to be orbitals. Orbitals come in 3 or 4 flavors, S, P, D, F. Those orbitals have funky shapes. They cumulatively lay on top of each other. They look like one big sphere. That's what we draw. An atom is a spherical object, but really it's just a bunch of electron clouds laying on top of each other. Well, that works. We'll figure this out later. Okay. So that's going to give us some idea of why we're drawing as a sphere, but really it's about the electron clouds that are within the sphere. So we are going to talk about the behavior as well, but like I said, behavior is all about stability. So an electron is going to be removed or gained in order to give stability to the atom. So many times those things are going to be related to octet. So why is something forming an anion? Why is something going to be forming an anion? Because it wants an electron to have a noble gas electron configuration. Why is something forming a cation? Because it wants to get rid of its one and only valence electron to form octet, the noble gas electron configuration. So all these things are really related to stability. And so the reactivity that goes along with why does this happen and why does this happen gives certain properties to different groups on the periodic table. So what's the first group called? Alkali metal. Didn't we just mess with that last week? What happened? Way reactive, and it one word, fire. Okay, so it caught the water on fire. Why? Electrons, give me more. It only has one valence electron, right? It's in group 1, all of those end at some number, S1. If you got one valence electron, just react the electron away, give it up, and then you can be stable. And that's what happened in that experiment. It reacted very vigorously. But then group 2 has how many valence electrons? 2. Group 3 has 3. What's the type of group 3? Say again? Boron, thank you. Group 4, carbon, has 4 valence electrons. Group 5, nitrogen, has 5 valence electrons. What will 5 valence electrons force that atom or those atoms to do? Gain 3, not lose 5. Because you're going to go the shortest distance. And that's why everything on the left of carbon will do what with their electrons? Lose, because they have 1, 2, or 3 valence electrons. Everything on the right of carbon will gain electrons because it's too much effort to lose 5 or more. Instead, they just gain the extra electrons they need. All right, so everything that's about chemical reactivity is all explained by the electrons. So, who is this? Vanadium. Okay. Vanadium, 3d3. How many valence electrons does vanadium have? Why 2? Wonderful. Okay, so this is the part that everybody on my honors chem test messed up. Okay, 4 is the 4th energy level. 3 is the 3rd energy level. Who's the outer shell? 4. So the valence electrons are those in the outer shell, and that gives us a definite 2 valence electrons from vanadium. However, the 3, which is like, they're kind of like the d block, which are those d orbitals, they are just kind of right inside the 4th energy level. They're actually of higher energy. So there's this weird dynamic, like, yeah, they're the 3rd energy level, but they're of higher energy. So vanadium's actually totally fine, totally cool with getting rid of those 3 as well. Those are not technically valence electrons, but I'm going to put quotes on them. They're kind of like valence electrons. So technically, vanadium can form 5 charges. 1 plus, 2 plus, 3 plus, 4 plus, 5 plus, because it can lose all 5 of those if it needs to. Transition metals are the only ones with those abilities, right? They're the only ones we have, like, more than 1 charge. And it's usually because of some stability attained by losing a certain number of valence electrons. Now, orbital diagrams, you guys remember how to draw those? Arrows, draw it for vanadium. I will do an example, but I want to get you started first.
Do you show the first one like the 1 or 2?
So when you're thinking about the electrons are in individual orbitals. Those individual orbitals we draw as just a hash like this. We label it as the first 1s orbital. Each orbital holds 2 electrons, and that's it. One goes up, spins up, and one spins down. 2s has its own separate orbital. One spins up, one spins down. Now, 3p. How many total orbitals? 3 orbitals exist in the p sublevel. Hear that vocabulary? 3 orbitals, 1, 2, 3, exist in the 2p sublevel is what it's called. How do you know how to fill up an electron configuration? There are 3 rules. So when you say up all the way across, how many am I putting into each of these orbitals? Oh, one at a time. Whose rule? Right. So the electrons are going to repel regardless, right? It's like these have to go together. Dang it, there's 1 orbital. These have to go together. There's 1 orbital. If I want to fill these up, I use whose rule says 1 at a time. Hans One's rule. Do you remember that? Hans One's rule. Hans One's. Okay. I came up with really stupid things to help me remember them in like 10th grade, and I still remember them. It worked. Yay. Okay. Hans One's. You fill in 1 electron at a time in each of the orbitals. Then you polypair them up. Pauli exclusion principle means that you can only fit 2 a pair, polypair, electrons in each of the orbitals. And so you're like, okay, well, why did I have to do that? For practice, because you were going to fill them up anyway, because we still have more to go. But if you stay in that practice, you'll always do it right. Off-ball, which I think I heard somebody say, off-ball, awfully low. Okay, so those are my 3 phrases. Off-ball, awfully low. I start off at the lowest energy level, and then I go to 2, 3, 4, 5. Sequential, right? That's common sense, but off-ball's principle means you start off at the lowest energy level. Poly pair means you can pair them up. That's it. No triplets, no quadruplets. Tons ones, you fill in one at a time. All right, 1s2, 2s2, 2p6. What's next? 3s2. Next. Draw 3 orbitals. 3p. Fill them up and then down. Okay? And then I get lazy. I do half arrows. You guys can do the same. And then what else? 4s2. And then how many orbitals? I have to draw all 5. There is no choice. We will draw all 5 orbitals in the 3D sublevel, and then do what? 3 up, that's it. Do not get crafty and try to put 2 in a bed together, okay? All right, so in that case, I can see, it looks like I have 3 free electrons, which could be lost, possibility, but certainly the 4th probably would be lost first, or the 4s electrons, yeah. You can only, you're only supposed to do it for the electron configuration. So his question is, can I do a noble gas shortcut? Yes, unless I state otherwise. So what's the noble gas shortcut for vanadium? Go back to the last noble gas you passed from vanadium. So back it up. Argon was the last noble gas. So if it's bracket argon, what of the electron configuration does that consist of? 1s2 to what? So basically, when I put a bracket argon like that, that means blah 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 blah, and then you fill in the rest. 4s2 3d3. So this is acceptable if it doesn't state that you have to do the long form. Okay, and so that's very helpful when you're doing like uranium, tungsten, bismuth, things like that on the bottom of the periodic table. So far, remembering okay? It's probably a little fuzzy for some of us. Okay. This is more about reading. Electron configurations show how the electrons are thought to exist around the atom. In the orbitals, orbitals is the word for quantum orbit, is the term for 4. So the N number, which is the first number we list, like for example 1s2, this is the first quantum number. We will actually talk about quantum numbers more in depth maybe today. And there are a lot of different ways to state that number. And so don't get confused, the vocabulary is pretty robust. N number, principal quantum number, the period number many times are what we refer to that 1 as, because that's the first period along the periodic table, whether you're just saying energy level or shell. Take your, or pick your poison, any of them will work, but just note that they all mean the same thing because it's pretty, it varies throughout the text and how you read them. If you ever hear the word subshell, it's more referring to the letter within. Now, there's not really a subshell S because that's the only shell. S is the shell because there's only one orbital. It would really be most appropriate for like P or D or F. Oh, so energy in that subshell or shell, okay? And then at the end, we should be able to really find where are the electrons, valence electrons, the ones that are most reactive, and what's going to happen to them. Are they going to gain? Are they going to lose? Or are they going to stay the same? So that's kind of the thought behind electron configurations. And then this is off-falls diagram. What was off-falls rule? Off-fall, awfully low. You start with the lowest and then what? Work your way up. So if you remember that when you hit D block, you -1 from the principal quantum number or the shell number, you're good. If not, you have to memorize off-falls diagram. Okay? 1s, 2s, 2p. So far, so good. 3s, 3p, 4s. So remember I told you that 4s was lower energy, 3d was higher energy? It's just a smidgen. You can see it, but that's why we don't go straight 3s, 3p, and then 3d. It's because of the energy differences. That's the reason behind it. That's why that reads this way. Is that clear? Okay. And then there is another fact to notice is, sorry, I did not erase these. I thought it would be quicker, but you know what? I'm just erasing now. So as you're looking at the off-falls pyramid or diagram here, you should notice a very large energy gap between energy levels 1 and 2. It's much larger than the energy gaps between 2 and 3, 4 and 5, and so forth, right? This gets very, very compact as you go up. That means that the largest energy differences are between energy levels 1 and 2. So if an electron drops from like n is equal to 2 to n is equal to 1, there's an electron dropping from excited state. Do you remember this at all? Excited state to ground state. Okay, if that happens, energy is released. You already told me that. But if you had to compare how much energy was released between n is equal to 3 to 2 or 2 to 1, who's going to release more energy? 2 to 1, okay? It's just simply because of the gap in energy that's associated with those energy levels. It's really because energy level 1 has electrons, right? All the energy levels have electrons. Who is that closest to? Who's energy level 1 closest to that will be attracting it? What's inside of the atom? Dead center. The nucleus. So it's because this is so attracted to the nucleus, it's actually closer to the nucleus than it really wants to be, simply because the electrons in that cloud are attracted to the positive protons of the nucleus. So it's holding it in, it's sucking it in, and all the other ones are kind of free to go. So that's why there's this larger gaps up there. But as a kind of intro, if I have a high amount of energy, that photon or that light, whatever energy is released as this electron emits energy, it can be in many different forms of energy. What were some of the energies on the electromagnetic spectrum? Shout them out. Visible light, what else? UV, IR, radio, gamma. What else? Microwaves, come on people, we use that daily. So, X-rays, so all these forms of energy, right? Some have really, really high amounts of energy within it, which makes them very dangerous. Who are some of the most dangerous forms of energy? Gamma, okay, because you could become the Hulk, or too much UV gives you skin cancer. What else? X-rays, you can learn so much. That's why people, you guys know people wear the little radiation detectors, like at the hospital. You guys gotta get out more. Okay. So nurses, okay, whoever gets a lot of X-rays, they'll wear these little radiation detectors. So my sister had one because she worked in pediatrics doing stuff with like, people that make you little babies, like just horrible situations. But anyway, if they get too much exposure to radiation, they can't work. So it's because it's a health, they can't work for like the rest of the month. You can only get so much radiation exposure per month. So, but I'll tell you, fun fact, your bananas, potassium-42, radioactive. So we're exposed to radiation all the time. It's just sometimes we get too much, yeah.
If you don't work for the rest of the month, you should get paid for the rest of the month?
Yes, probably, but they have to work out schedules. Or you switch roles and you don't get exposed to radiation. Yeah. So, kind of reeling back in here, energy comes in many varieties. Energy comes in many ranges. Low energy waves, high energy waves. You guys just told me the most hazardous ones, like gamma and so forth, those are high energy, okay? Low energy ones would be like what? Radio. So who listens to like 95.1? Okay, 102 jams. Okay, so all these different radio stations. I listen. What's NPR?
No idea.
90.7. Thank you. So all these are all different megahertz. It's just a frequency coming into the radio. Well, that frequency is related to the actual wavelength. Radio waves are like 100 meters, really, really long. How fast am I moving?
Very
slow. Do I have a lot of energy?
Not at all.
No. Okay, so long wavelengths have. Yes, they do. Long waves have long. Long wavelengths have what kind of energy? Low energy. What kind of frequency? Make a choice for you. Well, frequency is the number of times you pass a spot. So if I was like long and slow, I wouldn't pass this spot very frequently. But then you're gamma, and you're like really, really fast, really, really small. Okay, so short wavelengths, high energy, high frequency. Those relationships should be like that. You should know like the back of your hand. So now let's jump into those details. So I told you this is kind of a fast and furious day, but I'm trying to hit the highlights of everything because you guys need to probably do some specific reading. Energy? No. Darn it. Okay. Can I get to energy? Can I get to energy? I'm not ready for energy yet. Pause your energy thought. We have a lab with that tomorrow too. So, all right. So here's your periodic table. Your best friend. You've seen it for 3 years. You know the representative elements. Those columns. Those are the big towers on the periodic table. So if you were like, what the heck's a representative element? It's just the groups 1, 2, and then 3 through 8. That's just what those are called. It's just a category. and it's because they're representative of everybody in their group. Their properties are carried throughout the group. So, for example, a property of group 1 is highly reactive with water. Group 2, what's something common between some of these? React with water to form bases, somewhat strong bases. Group 3, they have some interesting characteristics like metalloids, used in electronics, something about electron flow. Group 4, they form network covalent structures, most of them. Group 5, yeah. Group 6, they don't have a specific property except for the fact they have 6 valence electrons and likely form a 2 charge, or 2 negative charge. Fluorine in category, mostly very reactive because of its one electron missing from its octet. Noble gases, fairly inert. So I'm just saying they're representative because they generally carry very similar characteristics. D block, F block. Okay. Okay, here's the part that's new. So we talk about electron configurations a lot in honors chem. Some special situations cause electron configurations to deviate from what our expected prediction would be, and it's mainly to do with stability. So, would you say, as an example, this is D block, okay? This is D orbitals. Would you say that this is stable, or this is more stable? It's the second one, because if you can have an electron, one electron in every single orbital, no electrons butted up next to each other, there's no extra repulsion. They say, and this is kind of on, the jury's out on this. I know, they're like chemistry politics here. But this is supposed to be a half-filled sublevel. It's supposedly going to have more stability than a not half-filled. And certainly more stability than like this. That little extra electron there is causing some repulsion between these two. So most of the time, electron configurations will prefer to be full sublevel or half-filled sublevel, none of that stuff in between. So the 5 electrons there or the 10 electrons there will be most stable. So how do they make it happen? Copper, for example, will do a promotion. And so it's S sublevel, it's 4S right here. Notice that copper is 1 away from fulfilling all of D block, right? So it's right next to zinc. It's got 3D9 as its final valence electron count, or final electron configuration. What will happen is this S will promote an electron up to fill D block, because it's the highest energy level, so it wants it to be very stable, so it's not so reactive. So instead of being that, it'll be what? 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Okay, so 1, you can still tell this is copper, because how many electrons are there? 29. It's still 29, so still copper. It's not an excited state of copper. Why? Yeah, we didn't jump to like a super high energy level. We didn't even jump we didn't jump to a higher energy level whatsoever. We just put 1 in an energy level that it already had. It just wasn't filled. Okay? So this is called electron promotion, and that's because it wants D block to remain stable. But what does that do for copper? That means copper can form 2 charges. Either, or are its true valence electrons here in this first example? 4s2. So if I lose those 2 electrons, what's my charge? Copper 2 plus, okay? Copper 2 is what color? Blue, okay? So that's a fun fact you should know. If I look at this electron configuration, what would be the likely charge copper would form? It would lose that 1 and become copper 1. Have you heard of any other charges of copper? No, there are no other charges of copper. These are what they'll lose. They'll lose either those 2 and say, screw you, D block, you're just going to have 9, or they'll promote 1, lose that last 1, leaving extra stability because the D block here has 10. Okay, so that's why those charges occur. It's not just because of magic. All right, so where else do you see those? Look at chromium, copper, molybdenum, I can't say that one. Rutherfordium, and palladium. And I want you to think about what could actually be found. Go ahead. Told you it's a talky day for me. Bear with me, guys. Anybody have any guesses? Chromium? What will chromium do? Promote 1 to become what? 3D5. It'll be a half-filled D block. What about copper? Okay, we're going to do molybdenum. Same as chromium because it's right under chromium, right? Same general electron configuration. What about rutherfordium? Where's rutherfordium?
No, can't lose one?
Where's this one?
It's 2 away from the moly. It's right under iron.
Okay, 1 away.
It's right under iron.
It still could promote, we'll see. And then palladium. Okay, so what we expect is just our normal expression. What we see is this. And it's because it's going to sacrifice and try to get either a full filled or a half filled. What's up?
On the bottom right, if it does promote it, do we still have to write the 5s 0?
No, but it helps me see that you know what the heck you're doing. Truly. So it sacrificed the 5s2 to give stability to the higher energy level of 4D. So it made 5s1 and 4D7. And then this one actually, palladium gave up 2 to give a full D sub level. Yeah.
So you can charge it palladium.
Where's palladium at? What number is palladium?
It's right next to rhodium, under nickel.
46. It possibly could be 2 plus because of this first 2 here. That's probably about it, really. It could be a 2 plus. Yeah, that's likely it. Because there's not, in palladium, it doesn't form. It's used as a solid metal. It doesn't want a lot of charge. Okay. All right, so I'm going to talk to you guys about some terms, and then we're going to do light equation stuff, and then I'll finish the rest of this tomorrow, okay? So paramagnetic and diamagnetic obviously relates to magnetism, the words in the term. But then you have to memorize what the 2 terms mean, as well as why does it matter. So this was a term that you read about in your reading, but paramagnetic just simply is going to say that, I always say this wrong, I was going to say para means polar. That's how I remembered it. Okay, para means polar. That's it, right here. So para means polar means that we'll have a polar end of the atom and a non-polar end of the atom, simply meaning that the electron configuration doesn't have every single electron paired up. You saw us spinning one up and spinning one down. That's what the arrows were representing. That actually means that one spins clockwise and one spins counterclockwise. So when you balance that with a clockwise spin and a counterclockwise spin, you don't get like a magnetic pole on the individual electrons, even though they're negative. Basically, they cancel each other out. If everything was paired up, we'd be fine. But many cases, which is predominant, most of the periodic table, will have at least one unpaired electron in an orbital. That will leave a residual charge or magnetic pole on that atom, on that single atom. And so when a lot of atoms get together, they show a really magnetic pole, or a higher magnitude because it's summative at that point. So that summative magnetic pole we can take advantage of. You know, we can use it for different reactions. We can use it for, you know, think of what are my magnets made out of? You guys know what these magnets are made out of? These really strong magnets? Like, there's that strong of a magnet? Neodymium. Neodymium's in, what should know, is ND?
Yes.
Where's it at? Oh, 60, okay. So if you see it's in the middle of F block, that's just going to be something F3, right? You're going to have 3 unpaired electrons in F block. So it's definitely magnetic. So if it has a unpaired electron, it'll act polar, meaning it has a positive end and a negative end to the atom. Creates a magnetic pole. And then diamagnetic, I just say diamagnetic don't, okay? They just don't. And so it don't attract to the other side. It doesn't have a pole. And so it has everything paired up. So if you want to remember it through my little silly ways, paramagnetic acts polar, meaning it has a magnetic end, or a positive negative end. That's what polar means. Or diamagnetic, don't. And just do a little sassy thing with it, you got it, okay?
Don't.
So that means because everything's paired up accordingly, there is no pole left, or there's no charge left over. So what is something that's not magnetic? Look on the periodic table, something that's all paired up. Zinc. Zinc's not magnetic. What else?
Cadmium. energy.
Yeah, go down that little family. Zinc, cadmium, mercury, copernicium.
No, that's not francium.
What else?
Probably something like neon,
Well, those are gases. Those are
and probably something like
look at your metals.
calcium.
Calcium, magnesium, strontium, barium, blah, 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 that whole group.
What about like manganese? No, not here. It's all those stuff.
Yeah, manganese would have a 3d5. Those are 5 unpaired electrons. That's a large amount of magnetic field.
It just says
Yeah.
set.
There's only a couple of groups that are diamagnetic. Yeah.
Would all the alkaline metals be like non-magnetic?
No, they are magnetic. Because they don't have paired, right? There's only one S
Oh.
or S1. So they're paramagnetic, not diamagnetic. Yeah.
So group 12 would be the only diamond.
Group 12?
Or right now, what would you
No,
say?
all of group 2, because they're all paired. All of whatever Zinc's group is, 10, no, 12, yeah, all of them. And that's what, as far as I go, because the other ones are not metallic. All right, and then talk about that. Excited state, ground state, we briefly talked about. We're going to apply those for more in the lab tomorrow. So let me tell you, I'm going to go straight to something else. I'll come back to that. Okay, light equations, right? You need to memorize the order of the electromagnetic spectrum. Ready? I got it. Just wait. Gonna X your voice in my radio. Gonna gamma X ray. Your ultraviolet. Voice visible in IR. My microwave radio. Okay. I have to come up with really stupid things. I'm going to keep repeating that. It's not me. It's for you. Okay. So, gonna X your voice in my radio. I have no idea what that means, but it works. Gamma is the what energy? Highest energy? What wavelength? Shortest wavelength? What frequency? Highest frequency. It moves fast. Speedy Gonzalez, right? It's moving super duper fast, which is why it has high energy. These should be correlated. These are inversely related. Radio, lowest energy, longest wavelength, because they're like 1,000 meters long. They're huge. They travel above us. Highest wavelength, and then frequency, lowest frequency, meaning it moves really slow. Moving slow, low energy. Those two should correlate. All the stuff in the middle correlates. Okay. So what two equations come to mind with light? E equals. Okay, I'm ready. I'm gonna wait for a definitive answer though.
Isn't it E equals lambda over?
No. Oh, that's one. Do them separate. Give me the two separate. What's the speed of light equation?
Or not that one, not that one.
Thank you. I think it's on the very first page of your reading. Okay. C is speed of light. Write this down for yourself. C is equal to 3.00 times 10 to the 8th units meters per second. Okay. Lambda, that little upside down Y thing, that means what? Wavelength. Okay. And wavelength is generally going to be expressed in what unit? Length. Okay, say it again. It's either going to be meters or nanometers. If it is in nanometers, you must convert it to meters before you can plug it into this equation, because then your units won't match, and then I'll yell at you, right? All right, so then what's V? Frequency. Okay, so frequency will be measured in what unit? Hertz is a nice way of saying it, but I don't think it gives you any context. So Hertz is just because some guy named it, his name was Mr. Hertz or Dr. Hertz. Okay, but what's the true, give me the SI unit. Cycles per second, right? So we many times just don't express the cycle. We just say per second, meaning second to the negative first, or 1 over second, or just slash second, which is understood to be per second, aka Hertz. All right, so that's the speed of light formula. That is if you have a frequency, you're finding a wavelength, or you have a wavelength and you're finding a frequency. All right, so we'll get to that one in a second. What's the energy equation? Say again? E times 8, or E is equal to okay, I can do N. I'll tell you the N part in a minute. Let's go back here. E is equal to, forget the N, come back to that. H times frequency. I'll tell you about the N in just 1 second. Okay. E is energy. That's equal to Planck's constant, which is times 10 to the negative 34th joules times seconds. So that's what H is times frequency, which what's the unit of frequency again? Cycles per second. I'm going to write that as 1 per second. What happens to seconds? Cancels out. What's left? Joules. This E is the energy in joules of a photon. A single photon. Okay, so I can calculate the wavelength of one photon traveling. I can find the wavelength, the frequency, and the energy. But many times, sometimes it'll ask you for that, how much energy is a mole of photons, hence the N here. So if you have an N, so if you have like 2 moles of photons, you have to times that using what number? What number is accounting for a mole of things? Avogadro, 6.022 times 10 to the 23rd. So we'll use that in an example. That's what the N is referring to. Sometimes it'll just say the energy of 1 photon, though, and that's just straight up this. Do not accommodate for the moles yet. All right, so what's the connecting variable? Frequency. So you could combine these into one equation, use it for frequency. Does anybody have their AP reference to have it accepted? I thought it had this on. Yeah. So on the very you have you're like a colorful one. On the upper right hand side, it says atomic structure and it says E is equal to HV and C is equal to Planck's frequency. It gives you the definition of variables. So they expect that you know how to use these. It's just they give it to you as well. Okay. All right. This will be the last thing. I don't think I'm gonna finish what I need to do, but I think that you guys can still practice. So you guys see on your Let me find this out. I have 2 things I want you to start. And star these or highlight or something, okay? Where it says on page 3 of your packet, TB, so textbook page 337, atomic structure problems, you see that? Okay. Do 39, 40, try 45, I want to see effort, okay? 52. So basically 39 through 55, because the other ones you can't do yet. So 39 through 55. 39 through 55. Got it? Say again? Yeah, including 55, because that's, I was basically just looking for the light equation ones. And then turn to the next page, which is page 6. So you're doing 39 through 55, and then you're turning to page 6. And you see that little problem set that says electron configurations, quantum, and more. Hey, you guys can do as many as you're comfortable with, which is probably not all of them, but I think you can do most of them. 1 through 13. Some of them are just subatomic particles. Some are writing electron configurations. You probably should be able to do most of those in your sleep, I hope. That's why I wanted you to read so that we could get through in class. I thought I was explaining a lot more than I should have been. All right, the last little bit of your time is yours. Go ahead and try to start on one of these, okay? And then somebody text Vinky and Sean and say, Emma taught the entire time. Occasionally I have to.
Yeah. So it was terrible.
Should you guys